Hello and welcome back to Educator.com and welcome back to physical chemistry. So today we're going to talk about the properties of the Helmholtz and Gibbs energies. Let's jump right on in. Okay, so for the Helmholtz energy, one of the fundamental equations that we have is the following. We have dA is equal to minus S dt minus P dV. Okay, so in this particular case, the temperature and the volume are the natural variables for the Helmholtz energy. So, essentially what we're saying is that the Helmholtz energy is a function of temperature and volume. Now, we can go ahead and express the total differential this way. dA, this is the general total differential. It is going to be dA dt, we already know this, holding the other variable constant, not pressure. It's volume, dt, plus the partial derivative with respect to the other variable, dA dV, holding that one constant, dV. So this is the general total differential. This is the one that we actually extracted from the fundamental equation of thermodynamics. This is one of the four fundamental equations of thermodynamics. Now, if we equate this and this, and this and this, here's what we get. So, equating the differential coefficients, excuse me, equating the differential coefficients, we get dA dt with respect to V equals minus S, and dA dV, holding T constant, equals minus P. Okay, so basically what this says is that for every unit change in temperature, the change in the Helmholtz energy of that system is going to equal negative of the entropy. So what these negative signs tell us, so this is a rate of change. The rate at which the Helmholtz energy changes as you change the temperature is going to be the negative of the entropy at that moment. That's all this is saying. If you make a change in the volume of a system, the Helmholtz energy of that system is going to equal the negative of the pressure of that system at that point. And again, here you're holding V constant, here you're holding T constant. So because of these negative signs, this is what it means. So because of the negative signs, these equations, they say the following. Number one, an increase in the temperature implies a decrease in the Helmholtz energy. That's what this negative sign means. If you increase this, well, this is dependent on this. So if this goes up, this negative sign means that this goes down. So an increase in temperature implies a decrease in the Helmholtz energy. Now, the higher the entropy, the higher this value is, the more quickly the Helmholtz energy decreases. So again, it's really, really important when you see equations like this. You're equating something, some value, you're equating it with a rate. This is a rate. It's very easy to forget that we're talking about a rate of change. So an increase in temperature implies a decrease in A. The higher the entropy, the higher the entropy. In other words, if S itself is a bigger number, the higher the entropy of the substance, the greater the rate of change. The greater the rate at which A is changing when you change T. When you change T. That's it. So let's say I'm at a particular temperature, and let's say that my system has an entropy of 50 units. If I raise the temperature by a certain number of degrees, the Helmholtz energy of that system is going to decrease at a rate of, it's going to decrease at a rate of 50, let's just say joules, 50 joules per degree, Kelvin. Now, at that point, if my entropy was actually higher, if it was 100, then at that point, it's going to decrease by 100 joules for every degree Kelvin. That's what this means. So the rate, the higher S is, the faster something is going to drop the negative sign. That's all this is saying. Okay. Now, the second one says exactly what you think, based on what we did for the first one. An increase in the volume implies an increase in the volume implies a decrease in the Helmholtz energy. So an increase in V implies a decrease in A. I just have to make sure that I'm keeping all of my variables clear here. I have T and I have, yes, okay, good. So what this says, and the higher the pressure at that moment, the higher the P, again, the greater the rate of change. In other words, the greater the rate of decrease. The greater the rate of change or decrease. If I'm at a particular temperature and if I'm at a particular pressure, if I change the temperature, the Helmholtz energy is going to change by whatever the pressure happens to be. That's going to be its rate of change. If the pressure is higher, the rate of change is going to be bigger. The decrease is going to be bigger if I'm increasing the temperature. And it's the other way around. If I'm decreasing the temperature, it's going to go the other direction. The Helmholtz energy is going to increase. So that's all that this is saying. It's very, very important. Again, we're talking about what we want to do here is we just want to cover every single base possible. As far as chemistry is concerned, we're going to be concerned with the Gibbs energy. We're not going to concern ourselves with the Helmholtz energy, but we need to know that it's there. So if for any reason we decide to run an experiment where we're actually holding temperature and volume constant, then we have to use the Helmholtz energy and not the Gibbs energy, because the Gibbs energy is for conditions of constant temperature and pressure. And constant temperature and pressure is what 99% of all chemical reactions are run under. So that's the standard laboratory conditions for chemistry, not for other things. So, okay. We're going to do the same thing for G.